Hello everyone. I'm Michal Trojanowski from Curity. I wanted to start this talk quite commonly with the question, how we achieve security. And if I asked you for a one-sentence answer to that, I would probably get many different and probably all of them correct answers. But from an API perspective, from the stock perspective, what's important for me is that achieving security means making the life of an attacker harder. So we're not able to 100% bulletproof our APIs. So we just want to make sure that it's hard enough for the attacker to eventually drop any attempts of attacking our APIs and maybe go to somebody else, or maybe they will change, the profession. And that's exactly what the financial-grade API security profile is about. It tries to make the life of the attacker harder. It's an OAuth security profile, which means it's a document that gives you a set of requirements and recommendations on the configuration options that you should use or the OAuth extensions that you should use and how you should use them in order to make your APIs and your product more secure. Originally, it was created with financial institutions or FinApps in mind. So it was targeting the APIs that the banks exposed with your bank account information and APIs that allowed you to make transactions. So it was really some high-value APIs. But the community that was working on that security profile soon found out that, in fact, the solutions that they propose, they can be used in any scenarios in any industry. So it doesn't really matter if you're in finance, if you're medical, or if you're dealing with any sensitive data. It's worth giving FAPI a try, having a look at that document. Also because it's really not a very long document, so you can read it quite quickly. In fact, when we think nowadays about data, most of data becomes sensitive data. Even if your application only processes things like user emails and their names, if someone is able to breach your API and harvest these, then maybe they will be able to use that to perform some more sophisticated attacks against some other APIs that have some more sensitive data. So in this sense, we should all think of our data as actually sensitive data. And in this talk, I will talk about some solutions that FAPI provides, and these will be solutions that are described in FAPI 2.0. Even though the official version is 1.0, the financial-grade API security profile. But I will talk about the second version for two reasons. First of all, FAPI 2 is just around the corner. It's in the last stages in the publishing pipeline, so it should be published very, very soon. And also, because it's simpler than FAPI 1.0. There are some solutions that they dropped, and you don't have to use them anymore. And in fact, after FAPI 1 was published, the industry found some vulnerabilities, some vector attacks that could still be used against the solutions described in FAPI 1, and this has been solved in FAPI 2. So if you want to have a look at it, go ahead and check the second version. By the way, the name actually has changed to FAPI now, and it's called FAPI, not Financial Grade API, because the working group don't want people to automatically associate FAPI and that security profile with just financial institutions and financial data. So how can we achieve that security? How we can make that attacker's life harder? First of all, there are some sensible defaults in the profile. For example, never put your tokens in the URI, whether it's in the request or in the response. In the response, meaning, or when can the access token end up in the response or an LED token? If you use OAuth flows like hybrid flow or implicit flow, then you will have the tokens in the response, and you shouldn't do that. Just use the code flow. And whenever you make a request to an API, always put the access token in headers, never put it in request URIs. Why? Because whenever the token is in the URI, it can easily leak into some logs, maybe browser logs, server logs, maybe some proxy logs. And if the token leaks, then it's easier for an attacker to get hold of that token and to perform an attack against your API. It also lists the algorithms that you should use for token signing and the key lengths that you should use with the algorithms, so it's worth checking what are the current recommended options. And many of these recommendations are actually very simple to implement. For example, this is part of a code in your API that you would use to verify tokens. So to limit the list of algorithms that you should use with your tokens, all you have to do usually is just provide some configuration to the library that verifies your tokens. So it's as easy as that. You just identify which algorithms I want to accept, and now your APIs won't accept a JOT token signed with a different algorithm. In fact, protecting the access token is an important part of FAPI. When an attacker is able to get a hold of your access token, they can call your APIs legitimately. It's actually what Dan was talking about, that then you're in a situation where you have an attack that it's really hard to notice, because it just looks as if the user was making the request to the API, because the attacker has the legitimate token. Part of the solution to protect the access token is ensuring the protection of the refresh token. So if an attacker is able to steal your refresh token, they will be able to get new access tokens and call your APIs. To solve that, always use confidential clients. Never use public clients, always use confidential clients. So these are the clients that need to authenticate at the authorization server. If you deal with mobile apps, you can use solutions like dynamic client registration or client attestation, so that the mobile app is a confidential client. And if you have browser-based apps, you can use solutions like the token handler, so adding a backend for front-end component that changes the client to a confidential one, and now you get better protection. And also, use strong client credentials. Don't use client secrets, because if someone manages to steal your secret, then if someone manages to for example, intercept the request to a token endpoint with the client secret, they will now get hold of that secret and will be able to perform more requests to the authorization server. They will be able to authenticate as your client. So what can you use instead of that? There's a solution called JOT client assertions. It is a bit more of code, but it's not that complicated. So this is client code. So this is on the client side. What happens here is that the client first creates a JOT. In that JOT, it puts the client ID and then signs it with the client's private key. Once it created that JOT, then it puts the JOT in the body of the request to the token endpoint, and when it calls the token endpoint, it authenticates with that JOT. So what happens now? Even if the attacker intercepts that request, they will only get that JOT, so they will only be able to make more requests to the authorization server for as long as that JOT is valid, and they won't be able to authenticate after that. Another solution for protecting the access token is using sender constraint tokens. So you want to ensure that even if someone steals an access token, intercepts it somewhere, they won't be able to call your API, because for standard constraint tokens, they would also need access to the private keys that are in possession of the client. So they have to break into the client, not only intercept a request to the API. There are two technologies that allow you to do it. You can either use certificate-bound access tokens if your client can connect with mutual TLS to the authorization server and to your APIs. Or if that's not possible, you can use a standard called demonstrating proof of possession. There is an attack vector that FAPI addresses where it uses a situation where the attacker can misconfigure a client. So you can have a situation where you manually put in the client or hardcode in the client the endpoints that the client uses to communicate with the authorization server. And what can happen here is that an attacker is sometimes able to inject their own token endpoint. So now when the user initiates the code flow, they will authenticate at the authorization server, the client will get back the authorization code, and it will send that code together with the credentials to the attacker's token endpoint. And now the attacker will be able to get your access token. To protect against that, always use metadata endpoints. So don't configure your client by hand. Just allow them to get all the information that they need to communicate with the authorization server from a metadata endpoint. Both OAuth and OIDC standardize metadata endpoints, so it doesn't matter which technology you use, you can use that. Of course, they have to be HTTPS protected so that nobody tampered with the response. And in fact, many client libraries support that. Here you have an example from Spring Security and Node Auth Assistant. All you have to do in these situations is just provide the issuer URI, and the library will know how to construct the metadata URL, because it's a well-known URL, and they will then query the authorization server and get all the information it needs to configure itself. Another vector of attack is redirect URI mix-up. So this one happens when the attacker manages to inject their own redirect URI to the authorization request. And what happened then is when the user authenticates or starts the OAuth flow, authenticates at the authorization server, but now the authorization response is returned directly to the attacker's redirect URI and not to the original client. To prevent that, always use push authorization requests. It is a bit more work to use them. Push authorization request requires you to make additional requests to the authorization server before you start your OAuth flow. And unfortunately, not many libraries support that out of the box, so it is a bit more of work. But if you're concerned with this type of attack, you should have a look at PAR. It's an extension to OAuth. Another vector of attack that FAPI targets is authorization code mix-up. So this one deals with a situation where the attacker manages to inject their own authorization code into the response from the authorization server, and then they trick the user to create the attacker's access token and do something in the name of the attacker. So, for example, send some money to the attacker's account and not to the user's original account. This is a bit of a sophisticated attack, but it can happen. And actually, protection from this attack is quite simple, because all you have to do is always use the authorization code flow and always use PXE, proof code for code exchange, So the OAuth extension that many of you, I'm sure you're using anyway. Pixie was originally meant for mobile apps and for public clients, but in fact, the industry found that it's a good way to protect the authorization code response, even for confidential clients. Many libraries support that. For example, the Node Auth Assistant always uses Pixie, and in Spring Security, Pixie is enabled by default for public clients, but for confidential clients, you just need to set one configuration option, and you're good to go. The Pixie is added automatically to your request. If that's not possible, if you're using a library that doesn't support that, using Pixie is also, it's not a complicated extension. It just requires you to add 2 parameters to your flows and persist one of them somewhere, so you can reuse that with your token request. So what I would like you to remember from that talk, regardless of your industry that you're in, have a look at FAPI. It's not a long document, and so you can read it quite quickly. And what is important, you don't have to implement the whole security profile. Just have a look at it, check what are the easy options, the things that you can easily implement. Maybe these are some just configuration options that you will switch, or OAuth extension that your authorization server supports anyway, and you just have to switch it on. Whatever option you will use from FAPI, it will make your solution more secure. So eventually it will be useful for your APIs. And also remember that protecting the access token is an important part of your API security. If you've been to Jakob's talk yesterday, in fact that was what he wanted to. He talked about as well. We can create really secure APIs. But then if someone can steal the access token, if someone can get hold of the access token, or can trick your users to authenticate as another user, or authenticate as the attacker, or hack into your clients, they will be able to get data from your API anyway, and breach your APIs this way. So thank you. That's everything from me. By the way, there's me and my colleagues. We wrote a book recently, or we're still actually writing it, about OAuth and security. So we talk a lot about tokens and security and some of this stuff I mentioned here today. There's an early access for it, so if you want to scan the code, you can get an early access to that book before it's released. Thanks.